So, we have looked at the Ising universality class of systems, for which we wrote down a Landau energy functional and from which we got the equilibrium configuration. Now, I would like to do that in a slightly more general context and show what happens when you introduce fluctuations on the one hand and the idea of inhomogeneities on the other, and how there will be relaxation to the equilibrium state. So, to recall to you, we begin right away with the order parameter m of R, the magnetization or whatever the order parameter be, and if you recall the Landau free energy it is not exactly the Helmholtz or the Gibbs free energy. We saw that we constructed a functional in such a way that you got the correct equilibrium value above and below the critical temperature. This free energy L, let me just call it L, this is equal to an integral in d dimensions of R, and then the terms inside, first of all, in the absence of an external field there is no linear term, but if you put in an external field there is of course a term proportional to that. So, let us put in a field H of R. So, this is minus H of R m of R, there is such a term, and the next term is a quadratic term, but if you recall it had a coefficient which was proportional to t minus Tc, so that it would give you the right critical behavior. So, that term, let me call it A tilde m squared of R, and this A tilde is a positive coefficient A times T minus Tc over Tc, which is A times T. Little t was this difference between this T minus T, reduced temperature T minus Tc over Tc, and in the magnetic case there was no cubic term but only the fourth order term, and the temperature dependence of that term, the coefficient, was irrelevant. It just had to be positive so that you would have stability about the equilibrium, stable equilibria. So, this was B times m to the power 4 of R, and then to include inhomogeneities caused not just by the fact that you have an H of R, but in general you have a term which gives you the gradient energy when you have inhomogeneities in the magnetization, and this was of the form 1/2, that half is just for convenience, some coefficient times gradient of m of R mod squared. Okay. So, that was the Landau free energy. The equilibrium solution is found by minimizing this free energy. So, equilibrium configuration given by delta L over delta m of R equal to 0. And we also have to ensure that it is a minimum rather than the maximum, but the structure of this makes it clear that it will be a minimum. So, what is that equal to? Well, we use the rule for functional differentiation, make this R prime everywhere, and use the fact that the functional derivative of m of r with respect to delta m of r prime, this is equal to a delta function d-dimensional of r minus r prime. That is the basic rule. Then of course, the only non-trivial term is this, and I argued that the functional derivative of gradient m of r mod squared r prime say divided by delta m of r, that is what you are going to have to differentiate out here. So, if you make all these guys r primes,
don't you want to put the integral also to go so that integral of the,
yeah, I need to do the integral as well, but let me look at what is going to happen here. This is going to be twice, so it is going to give you a twice gradient of m of r prime times derivative d or whatever it is of r minus r prime times the functional derivative of the gradient itself. But the functional derivative of, because it has got to be a vector, right. So, this is times dot product with delta over delta m of r gradient m of r prime. Okay. And this you do integration by parts. Yeah.
The delta is, should there be another derivative? There will be only one.
only one derivative.
Only one?
No, that's okay.
No, the Dirac delta will come out of doing the derivative, functional derivative.
Oh yes, yes. So you are right. The gradient of the delta function. Thank you. Yeah. I use this gradient with respect to r prime.
Yeah, put primes on them.
Yeah. So this is r prime out here. But what I really have is an integral over ddr prime, so really you should insert this d r prime on both sides, and when you do that and you integrate by parts, this delta function is going to fire and this gradient is going to operate on this factor here. So you got a del dot del and then you have del squared. There is already a half, so it just gives you minus del squared. Okay, so let us cut that short and write this whole rule as delta over. So once you put that in, we can write the solution down. So let us just do that. So this configuration is given by minus, I want to write this properly. So 2a tilde m of r prime plus 4 b m cubed of r, sorry the r, everything is r prime is gone, minus h of r minus c del squared m of r equal to 0. That is the equilibrium configuration. So it is a solution to a partial differential equation in space like the Schrodinger equation, but there is a non-linearity here. There is an inhomogeneous term which is not serious, but if you had just this term it would be nice, it would be linear, but unfortunately there is this non-linearity, okay, which you can't get away from. So the equation, the thing from the start, it is obviously a non-equilibrium situation, yeah, a non-linear situation, okay. Alright, now let us suppose we have solved this in principle, and now I ask the following question: if there is a local fluctuation, say due to thermal noise, from this equilibrium configuration, how does the system come back to it? So, this is now in the spirit of our old friend linear response theory, and we would like to find out what is the way the relaxation is going to proceed. Okay. And now there is no rigorous way of doing this except in a specific model, but you would guess the following exactly as we did in the very naive Langevin equation case. You would guess the following. You would say, well, a good assumption would be to say, okay, for a given configuration delta L over delta M, I am not going to write all the arguments, this quantity is 0 in equilibrium, and away from equilibrium for a non-equilibrium configuration this measures the deviation from the equilibrium. So, a good way to find out what the relaxation is like, a good guess is to say delta over delta T, a configuration M of R, relaxes to equilibrium by minus this times a constant times this deviation from the equilibrium. So, that is a relaxation equation, typical relaxation equation, exactly in the same spirit as we saw relaxation occurs in the Langevin equation or in the Boltzmann equation, etc. But there is no guarantee that you give a configuration, it does not relax to a local minimum. So, in general, once you give me an equilibrium configuration of this solved by this, there are local maxima and minima, and there is presumably a global minimum which is the thermodynamic equilibrium state. But if you give me a model of this kind with some initial condition configuration, there is no guarantee that it does not tend to a local minimum and stick there. That does not happen in actual practice, because if you plot this M as a function of configuration variable, it might have this kind of behavior, and if you start here you might relax simply to this point, whereas you really have a thermodynamic equilibrium state over there. So, it is clear there must be some fluctuations which take you out of these local wells and put you into the global minimum. Therefore, to this you must add a noise term which mimics the effect of fluctuations. But this noise must itself be inhomogeneous because it is a function of R, because you have got an order parameter which is a function of R now. So, it is a field plus eta of R and T. So, this is thermal noise. And this is exactly the structure of a nonlinear Langevin equation. But nonlinear. Okay. So, its solution is formidable because you have a stochastic differential equation for a field and it has got nonlinearities. It is space dependent, so it is a partial differential equation, space and time derivatives, and on top of it you have nonlinearities. So, it is formidable, and the only way you can make any headway with it is by functional integration methods. But we need to specify what sort of noise. So, we make the simplest assumption that it is uncorrelated Gaussian noise. So, we will start by making this assumption that eta of R and T over all realizations of this noise over all realizations, we will say that it has got, assume that it has got 0 average, and moreover, and here is a crucial assumption, eta of R T, eta of R prime T prime over all realizations, this is proportional to delta functions. So, we assume that the noise is uncorrelated at different time points and at different times. So, this is equal to some constant 2D delta of R minus R prime delta of T minus T prime. in d dimensions, of course. Okay. This is not so obvious, and I am slurring over certain technicalities here. For instance, if you have what is called a non-conserved order parameter, then this is no longer true, and consistency demands that you should put del squared over here acting on the delta function, but in the magnetization case that does not apply. So, this is okay as it stands. Then we need to specify the probability distribution of this eta. So, what would one do? You would assume that the distribution of eta, so let me call it P sub eta, the probability, yeah.
What is conservation in an order parameter?
This is not a quote unquote dissipative order parameter, it is magnetization, unlike for example concentration that relaxes to an equilibrium configuration, but there is no conservation of total magnetic moment or any such thing. Okay. So, there are two classes of problems, and if time permits I will mention the other class, but in this case this is a consistent thing here. Okay. So, you have P of eta of some configuration m of r of eta of r comma t. This probability is proportional to e to the power minus some variance, and because you got a 2d here you need to have 4d out here, integral d of r eta squared of r and t. So, that is the probability distribution of, it is a Gaussian probability distribution generalized to a field. This constant of proportionality, whatever is out here, is the normalization.
So, the volume will appear then.
It will be a functional integral over all etas. So, there would there will be some constant, and k inverse goes like integral, well, d eta e to the minus whatever it is 1 over 4 d integral etc. Okay. So, I am not going to get into, we will not try to normalize that, we just need the assumption that it is a Gaussian here, okay, which means you in principle know all the joint probability distributions as well. Once you make this assumption that is delta correlated, it is like noise. This is the sort of space dependent extension of white noise that we did in the Langevin equation. Okay. And we are now talking about the probability distribution of whole configurations of eta at every point r for a given, for each given t. Then not surprisingly one can actually write down a corresponding Fokker-Planck equation, because we need to know what is the probability distribution of m, what is the probability distribution of the configurations m of r at any time t given this. So, it is the old question exactly that the same as what we solved in the case of the ordinary Langevin equation. Given a Langevin equation, the statistics of this eta, the fact that it is Gaussian etc., how do you get the Fokker-Planck equation from it? Now, I just made the statement that we have in the original, in the other case, that we have a Fokker-Planck equation, we looked at its equilibrium and so on, but one can make this a little more rigorous. One can make this, one can do that fairly easily as follows, and we want to do this in this functional case. So, let us go about it in the following way. This quantity must obviously be equal to, by definition, the expectation value of a delta function, a generalized delta function of m of r t minus m of r for a given configuration minus the m that you get from the Langevin equation, so let me write it as MLE. By solving the Langevin equation for each value of the noise, each realization of the noise, and then averaging overall noise realizations. So, if I call that MLE, this is a function of R and T over eta. In other words, the average is of this delta function, we weighted with P sub eta. That is by definition the probability distribution of this configuration in M, okay, where MLE of R and T equal to MLE of R and 0, you give me the initial configuration and then you have to solve this equation. So, it is just minus gamma times integral 0 to t dt prime delta L.
Do you want the subscript LE for the at 0? That is what you give, right?
This is what I give.
There is no need.
There is no need for LE. It is whatever initial configuration you give, minus delta L over delta N. I will not write the argument here, plus integral 0 to t dt prime eta of R t prime. Okay. That is the formal solution. Of course, this quantity here involves that derivative with respect to L, so that is a formidable nonlinear object, but so it is not a solution, it is just a representation of this M, LE. And you have to put that, so everywhere here in bracket the argument is MLE in a self consistent way, of course. So I should really mark the argument, this is L of MLE. Okay. And then I have to take this delta function, multiply it by P of eta and integrate over all realizations, sum over all realizations, right. So that is the way one would do this, and you would of course start by saying, look, we do not write the solution down, I find the derivative of this with respect to time. So I am going to head towards a Fokker-Planck equation, and for that I need the derivative with respect to time. That will give me a derivative of this quantity. So it is a theta function to start with, and then there is going to be a derivative of this. So all the t dependence is sitting here, right. And for this quantity I go back and use of course the Langevin equation here. So that is the way you derive the Fokker-Planck equation for a given Langevin equation, even in the ordinary case, the finite degrees of freedom case. So the sum and substance is that you end up with the following Fokker-Planck equation. So you have delta over delta t p Pm of a configuration at any time t, this quantity is equal to, not surprisingly you are going to get gamma times integral d of r prime times gamma times that is the drift term. There was a minus sign in the Langevin equation, and remember in the drift term you get another minus sign, so that gives you a plus out here, plus, and the way we have normalized this with the 2d here, you have to do 1 over this guy. So this becomes plus d times delta Pm over delta M. Okay. So there is a second derivative term, because the noise in this case is not multiplicative, it has got pure delta functions, no R dependence here by assumption. So it is d times that, which is what you expect, plus this guy here. This is the drift term. The only difference is it is not linear. This thing is completely crazy, it is not a linear equation at all. But we can write down what is the equilibrium value, what is going to be the equilibrium distribution. That is found by putting this equal to 0, which is equivalent to putting this equal to 0. So the solution, the equilibrium solution, let us write it down. The equilibrium configuration, it is not a function of time. This fellow is obviously, apart from normalization constant, it is e to the minus gamma over d, because essentially it is equating this to 0, right. So it is e to the minus gamma over d times integral d r prime of r, let us say the function of r here. I am a little confused here because of the notation.
Delta L by.
No, it will be L, because I want to check if this equation is valid or not, right?
I mean,
So
if we just do this with the constant for
It's-
this one component.
it is just going to be L,
Yeah.
it is just L,
Yes.
right? Because if I differentiate it, I am going to get delta L over delta M here once. Right. But we would like it to be the Boltzmann distribution, right. Remember, this is the energy density, and you are going to have to integrate to get the full Landau energy. So it is of the form e to the minus whatever the energy, but we would like it to be the Boltzmann. So this goes to the Boltzmann distribution, which goes like e to the minus integral d dl minus 1 over k Boltzmann T, provided d equal to gamma kt. That is the fluctuation dissipation theorem, right. That provides a consistency check. Okay. I am sorry for using the same symbol d that we used for diffusion in the position space earlier. This is diffusion in the velocity space, the analog of that, because it is the Fokker-Planck equation for the analog of the velocity. If you recall what that was way back when, it was mv dot plus m gamma v equal to this force 8 of t, and we assumed a strength capital gamma for this guy here. So we assume that 8 of t prime was equal to gamma delta of t minus t prime, and then we got gamma as 2 little m gamma kt. But more important, remember the Fokker-Planck equation for it, we had delta of p of Vt over delta t equal to gamma times delta over delta V Vp plus gamma kt over m d2p over dv2. So this was the diffusion constant in velocity space. Now the m has essentially been put equal to 1, there is no m sitting here, so it is not surprising that you get d. Capital gamma plays the role of d, capital D here plays the role of gamma. Okay. So that's the way the consistency thing works out. Okay. So we have some idea.
The key statement here is that that exists an L from which that equation is coming.
Exactly.
That is the bottom.
Exactly. So there is a specific L, we model this L, we took care of the m squared term, the m4 term, the gradient energy term, etc., such that you get the correct equilibrium distribution, and we impose this condition here. Now the next question is to ask, how does it relax? How does it relax to equilibrium? That is a harder question, because you really have to go back and look at the Langevin equation itself, but that is a harder question. However, one can do the following.
Can you linearize around?
One can linearize, exactly. So we are going to assume, so relaxation to equilibrium, and let us do this in the simple case when T is greater than Tc. Because then m equilibrium of R, this guy is equal to 0. I use this for the average itself. So, right. I should really put brackets here, because I have used this m in the Langevin equation without putting brackets, but okay, let us be rigorous. This quantity is 0, right. Okay. So we write an equation for this m. If I go back to the Langevin equation, I have delta m over delta t, this quantity, a little bit away from equilibrium, is equal to minus gamma delta L over delta m, which is equal to minus gamma, and now you have to tell me what all those terms were. There was minus, there was a minus c del squared m,
Minus h of R.
so let us do it in the absence of an external field.
Plus 2 a tilde m.
Plus 2 a tilde m,
Plus we can throw like a 4.
plus there was a 4 b m cubed. I am going to throw this out. Right. We are taking average values. I am not going to indicate it specially. Everywhere there is average, so the eta term has gone away. So this is equal to gamma c del squared m plus 2 a tilde m. I am unhappy with the sign. Minus delta tilde m, gamma. Okay. Because there is a del squared term here and this m is space dependent, the obvious thing to do is to resolve it into Fourier modes, take a Fourier transform. Let me put a tilde for the Fourier transform here. So it says delta m tilde over delta t for a given k. Yeah. Okay. So this is Fourier with respect to the space variable R, spatial Fourier transform. This fellow is minus 2 gamma a tilde m tilde, and then this is going to give me a k squared, the del squared with a minus sign. So, there is going to be minus gamma c k squared, and I pull out the m tilde. Okay. Right. I do a Fourier transform here, I am going to get a minus k squared because it is I k the whole squared, and this is m tilde. Okay. So, this quantity is equal to, leaving out the nonlinear term. So, for small deviations from equilibrium, the linearized equation gives me this. Incidentally, this Langevin equation, this relaxation equation, the full nonlinear relaxation equation is called the time dependent Ginzburg-Landau equation in when applied to superconductivity. So, just this alone with the full nonlinearity is the time dependent Ginzburg-Landau equation. And then you add to it the noise term, it becomes a stochastic differential equation, and it helps you to analyze the way fluctuations lead to state of equilibrium. In principle, within this model, it tells you everything about the time dependent magnetite configurations. If you include the external field, then it tells you in principle everything. Okay. But whether the original assumption, this is valid or not, is a different question. It is clearly reasonable and plausible, sufficiently close to equilibrium, because you are saying the rate at which it relaxes to equilibrium is proportional to the deviation from the equilibrium. It is absolutely a linear response statement, just like Fick's law for diffusion or heat conduction, etc. It is a linear response statement. Okay.
It will be a linear response statement only when nonlinearity is
Linear in the field. It is linear in the field, not linear in the variable, not in the order parameter, no, but it is linear in the field. That is what linear response does, right? Okay. So, in particular it will give you some statement about the susceptibility, because remember the susceptibility is the derivative of the order parameter with respect to the field at 0 field. So, this thing is equal to minus m tilde over tau of k, where the relaxation time is given by relaxation time tau of k is given by 1 over tau of k equal to 1 over tau of 0, that is this term, plus gamma c k square. Right? Tau of 0, by definition, this quantity here is 2 gamma a tilde. So, the infinite wavelength or k equal to 0, the uniform background configuration relaxes at this rate with tau of 0. But this is equal to 2 gamma a times t, I should not use t, it is t minus tc over tc. And as t goes to tc, this goes to 0, so 1 over tau 0 goes to 0, and therefore tau 0 goes to infinity. That is called critical slowing down. So, this is where critical slowing down comes. Well, let us write that down. Remember we are in Tc greater than Tc, we started with that assumption. So, it diverges, goes to infinity, implies critical. For k not equal to 0. So, finite wavelength fluctuations even at the critical point will be okay, they will relax with the finite time, they go like k squared, 1 over tau k goes like k squared, okay. But as long as k, this thing is 0, if k is 0, then you have a divergence of the relaxation time, but the finite fellows do not do that, okay, which is reasonable. It is only the infinite long wavelength overall background mode that gets slowed down, okay. The shorter wavelength ones will have finite relaxation time, because those are controlled by this quantity. As this becomes larger, this is finite, and therefore you have finite relaxation time, okay. So this helps us formulate, it is a start of something called dynamic scaling, the dynamic scaling hypothesis. What we have therefore is the following, and from here
Say that the static exponents will have dynamical meaning.
yeah, the static exponents will get related, now we will see when you have, so let me call it dynamic scaling. So look at what tau k did, tau of k, it went like t, now let me use t for t minus tc over tc. For a minute, there is no time appearing explicitly anyway in this formula, so it should not confuse. This goes like t to the minus y equal to 1 for k equal to 0, right. And it went like k to the power minus z, these are standard symbols, z equal to 2 for t equal to 0. At the critical point, the other modes, the 1 over tau k was exactly proportional to k squared, and therefore tau k is proportional to k to the minus 2, okay. So we have introduced two new exponents y and z out here. Now both these can be subsumed in one relationship by again making a hypothesis that at the critical point this guy here is some power multiplied, and that close to the critical point this guy is some power law in little t multiplied by a scaling function, exactly in the spirit of Vidom scaling, right, and then experiment will have to tell you if that is correct or not, okay. So one hypothesizes that tau of k goes like t to the power minus y, that is this, in general, even when this kind of simple mean field theory is not valid, multiplied by some function of k times the correlation length, the old order parameter correlation length, to the, which is a function of little t. And now we need to get these two from it out here. For that you require, since, so let me write this fellow as in the critical region t to the minus y phi of k times t to the minus nu, apart from some constants, because this diverges like t with this exponent nu, if you recall, which was 1/2 in mean field theory, right. So how is this going to be reconciled with that? If you put k equal to 0, you should have this divergence here, which is this term here already, provided phi of 0 is finite. So we require of this function phi phi of 0 must be finite and non-zero, some finite constant. But as t goes to 0, this guy goes to 0, you want this behavior. That means this thing must be cancelled out with a t to the power y. So, we want phi of whatever its argument, phi of x, let us say phi of x, phi at x equal to 0 must be finite, and phi at x tends to infinity must go like x to the power minus y over nu. Right, because then this term will go like this, will then go to t to the power minus y, k to the power minus y over nu, t to the power minus nu to the power minus y over nu, which will give me a t to the y which cancels this and gives me a 1 over k to the y over nu. So, this goes like k to the power minus z, where z equal to y over nu, because remember we wanted k to the minus z. So, it is a simple trick, it is the same trick being played all over again, that you have two different limits, then it forces the scaling function to have this behavior. That is the only way in which you can be consistent here. So, this will immediately imply or y equal to z nu. So, this implies that this tau k goes like t to the power minus z nu phi of k t to the minus nu. So, we have introduced a dynamic scaling exponent z. There is one more exponent here. Now, we can relate this to the susceptibility, because what you need is the formula, the susceptibility chi t. Now, we do a Fourier transform of k omega. This fellow here is the derivative of m tilde in Fourier transformed in space and time and average taken with respect to delta h tilde of k. Right. So, we can now write, and we know that there is a gamma here, an exponent gamma, a divergence near t equal to 0 for the static susceptibility, right. So, once again we can make a statement about the dynamic susceptibility, make a generalized scaling hypothesis here. So, essentially you will have to assume that this fellow here is some power of t, little t, multiplied by a function of k xi and omega tau naught, where tau naught is this thing, the k equal to 0 relaxation time, right, and that turns out to give you relationship between this dynamic exponent and the other exponents, okay, and so on. Now, this whole business can actually be generalized to a much more general class of problems, including the way this is the beginning of the dynamic scaling theory, which is now applied to a very large number of problems, both in and out of close to equilibrium and far away from equilibrium, such as the growth of surfaces, spinodal decomposition, etc., etc. Okay. So, the wide variety, the trick is again the scaling. I have not talked, this is the starting point of the renormalization group approach to critical phenomena, which is where this comes into full play, the power of these scaling arguments. Okay. And you can rigorously show what the relations are between various scaling exponents, what the upper and lower critical dimensionalities are, what the nature of the critical point is in every case, etc. Okay.
See, it's we got all these static exponents by looking at just trying to, we got relations.
Yes.
When we tried to write everything in terms of the objects which came from the correlation length.
Right, right.
So now what we are doing is we have got from this thing, we have got something which is relating correlation length.
Yes, to correlation time.
Correlation time.
Exactly,
So Z
exactly.
is, I need only one more extra.
Exactly. So that's the whole point. Once you have a relation like that, we got rid of this intermediate thing y, and we already know nu, and the time behavior is given. This thing here will tell you what the
Is that
dynamics
all,
is.
Is it true for, it should be true for all.
With suitable modifications,
Z,
yeah, with suitable definitions of Z, etc. Yeah. The power of this whole thing is not apparent here, because unless you do the renormalization group, which is another way of saying that you use scale invariance. Near the critical point, the system becomes scale independent. All fluctuations on all length scales and time scales become equally important, and the trick was, as opposed to the original ways of tackling equilibrium statistical mechanical problems, where you try to solve or trace over a find partition function, you trace over all degrees of freedom simultaneously, this divides and conquers. So it breaks things up depending on the k value or the wavelength of the fluctuations, integrates over variables which either vary slowly or or very or long period times, long spatial extent, and then or the other way about, and then ask for a case, impose the condition that the system will look scale invariant on all scales. So that forces you to have certain relationships between various exponents, among other things, right. It also gives you a calculational method of computing systematically, computing critical exponents outside the framework of mean field theory. Okay. I use the symbol y and z here, although in the case we have looked at, y was 1 and z was 2, but the whole idea is that you hypothesize that these exponents can have different values other than these values here, okay. And indeed they do. There is a closely related to this Langevin equation, there is another one for growth of random surfaces, growth by aggregation for instance, called the KPZ equation, the Kardar-Parisi-Zhang equation, which again is like the diffusion equation with a noise term added to it. Okay. We saw the original diffusion equation was for a probability distribution, but now we are saying there is noise added to a diffusion equation itself. In the same spirit as this is already partial differential equations, and on that we added noise, a similar kind of approach there. Okay. That leads to so called roughening exponents and similar results. Okay. So I think I will stop here with this topic and refer you to some texts for the rest. Okay. There are a couple of good textbooks on this, many good textbooks on critical phenomena, but I will write out a list of these useful books and give it. Okay.